Hello, everyone. Thank you so much for joining us here at 4 o'clock on a Saturday at South by Southwest. We do have some really interesting stuff to share with you today, and I'm glad to be able to share it. We're going to be talking about reimagining energy use with digital technologies. If you looked at the send ahead for this session, you'll know that we're going to talk about more than that. We're going to talk about things like waste generation elimination. We're going to talk about greenhouse gas emissions and how important those things are. You will also have learned from that read ahead that 30% of our greenhouse gas emissions in this country come from the industrial sector. And when I say industrial sector, I'm really talking about manufacturing sector here in the United States. Talking about manufacturing, that's what we're going to talk about. We're going to talk about manufacturing in the United States. In fact, we're going to talk about an organization called Manufacturing USA. This is a network of nonprofit organizations that's been put together over the last 10 years by the federal government, in particular through NIST, the National Institute of Standards and Technology. And as we look at what they do, they're all focused on different areas of emerging manufacturing technology. And we'll take a look at here as they appear on the screen. You'll see that they're scattered around the United States, and you look next to each of the names and you see that they're really focused on a really wide variety of different emerging manufacturing technologies that are incredibly important for us as a nation, for national security, and for our economy. And it is a really wide variety of things they're looking at. Everything from a new way to make electronics, to biotissue fabrication, smart manufacturing, advanced composites, and the circular economy. So all kinds of really great stuff. Now, even though they're focused on all this wide variety of different things, they all share three guiding principles in common. Number one, they're to create an ecosystem around this type of manufacturing here in the United States. Think of things like supply chain and manufacturing adopters. They bring together, in a consortium fashion, subject matter experts from the government, from industry, and from academia to work together as a team to solve problems that are associated with these emerging technologies. That's number one. Number one goal is the ecosystem. But number two is, after doing that work together, it addresses number two, which is the manufacturing maturity of these different capabilities in manufacturing. Why? Because only when you do that will you make an impact on the nation and grow into high volume manufacturing, which is the goal. Now the third thing that these institutes are all focused on is securing human capital. And that's a fancy way of saying workforce development. You can have all of the technologies that you want and all of the machines and the equipment and everything else, but if you don't have the people, you're just not going to get very far. Now, workforce development, by the way, is one of the few things that our country has a real bipartisan feeling for. We all recognize this is a problem for a skilled labor force here in the United States. And I really, you can tell I'm getting kind of passionate about it. And we don't have a lot of time to talk. So I want to give you one quick example about why it's important here in the United States, and then we'll move on. You may have heard in social media or in the news about something called the CHIPS and Science Act, or the CHIPS program. This is bringing $52 billion together to bring semiconductor manufacturing and packaging back to our shores. Critically important for our economy and national security, again. If you think back to what happened with supply chains during the pandemic, it was pretty disastrous. We don't want that to happen. So, it's a big program, and the National Science Foundation recently released a report that indicated they project over 100,000 new high-paying jobs will be created by the end of the decade just by that one program alone. Fantastic, right? 100,000 great new jobs. However, the current pipeline with that kind of capability doesn't exist. Sure, we've got people in that pipeline, but not enough. So we've got a lot to do. I'm talking about semiconductor manufacturing, but really all sectors of manufacturing in the United States are desperately seeking a talented workforce. So I'm going to move on now. Hopefully you'll ask me sometime later about workforce development. I'm happy to do so. But that's enough about the background of why we're here. Let's get into the real meat of what's going on here with our panel. I'm going to start with me. My name is Art Wall. I am the Director of Fab Operations and Engineering at one of those organizations called NextFlex, not Netflix. I literally got, yeah, I know. I literally got asked that today, this morning. Somebody says, what, you work for Netflix? No, NextFlex. So we're the ones working on a new way of making electronics. And we do it differently by printing. So it's an all additive process. It's really cool. Plus, it satisfies some real big needs in medical devices, in aeronautics, in automobile, and several others. And that's kind of the reason, but when you do it that way, 3 really cool things happen. Number 1, you reduce the amount of water usage to create electronics. Believe it or not, you need a lot of water to do that. And you reduce it by more than a factor of 10. You also reduce the waste stream by more than a factor of 13. And we're here to talk about energy usage. By using digital technology, it reduces the amount of energy needed by a factor of 15. So a big deal for our capability in the United States, and I'd love to talk to you more about it, but I'm not gonna, because we're gonna get over here to our panel. Just one last thing, if you are a small business in Texas, we do have federal funds available to help you if you have needs in the electronics business. No more NextFlex. We're moving on to the important people on the stage. Okay, so I'm going to now turn my attention to these kind folks who have a lot more to tell you than I do. And I'm going to start at the far end. I'm going to start with Dale Brosius. He comes to an organization called IACME. And Dale, maybe you could tell everybody, what is the focus of IACME? What's your role within that organization? And if you can, give us an example of how digital technology has improved energy efficiency.
Okay. Thanks, Art. My name is Dale Brosius. I'm the Chief Commercialization Officer for IACME, the Composites Institute. What does a Chief Commercialization Officer do? It just makes sure that I wrangle all the cats, particularly our industrial, academic, and national lab partners, to point toward commercialization of the technologies that we're working on. I like to say, we're doing science, but we're not just doing science projects. So, these are not hobby horse projects by some professor at some university. It's really about how do we translate what comes out of those labs at the national level, university level, into the marketplace, and in the great pipeline of startup innovators that are out there. How do they get access to the talent and the resources needed to demonstrate that their technologies can make it to the marketplace? Been in the industry for 40 years. And one of the things I always notice, on my Flipboard, if I'm scrolling around, I see, this great technology is going to revolutionize batteries. This one's going to revolutionize something else. But if they don't make it from the lab to the market, there's never a gram of carbon dioxide ever saved. So, and that's really important, is to make sure we keep pointed on that. And I think that's where IACME comes in. So we have a large amount of shared infrastructure, large presses, analytical capabilities, testing, design, and so forth, that we make available to the marketplace. And we have the industrial partners bring things to us and says, I'm trying to get this out there. So we can form teams of supply chain members and move it toward commercialization. The other thing about those, we've got presses that can build full-size car parts, mold, and mold test wind turbines. So they're all at relevant scales, but they also serve as fantastic training facilities for engineers and technicians. So it helps fill that pipeline for skilled labor that we need. So, a good example that I'll talk about is how many of you here either drive an SUV or have driven SUVs? Yeah, almost everybody, right? Okay. What do you think the heaviest body part on that car is? It's that lift gate in the back. Okay. So mass in transportation means everything when it comes to fuel efficiency. If you can reduce the mass, you can improve the fuel efficiency of it. And so Volkswagen of America came to us with a particular problem they wanted to help solve, and that was learning how to lower mass on that large body panel. And they did it. They built the Atlas SUV in Chattanooga, Tennessee. It's about 100,000 vehicles a year. And as the whole Volkswagen platforms are moving toward electrification, moving away from petroleum engines to electric engines, they need to look at how do they offset that increased mass that comes from giant battery packs. And so they tasked us, let's take this particular component. And they had 2 targets. One was to get the mass down to something that would be equivalent to a stamped aluminum, so it's currently in stamped steel, and at a cost equivalent to steel, tall order. Stamp steel is pretty cheap. But we were able, through digital technologies, through empirical studies in the lab, and in validating what the software would predict in terms of the moldability of these materials, be able to design a liftgate that was 36% lower. Historically, 20% was about as well as anybody had done. But we designed one that was 36% lower in mass, that met all the requirements that a liftgate needs. And it's a lot. You know, there's impact requirements from crash, there's torsional requirements from, you know, when you lift it up on one corner or not, and then there's another requirement for when it goes through a paint line. So all the temperature requirements as well. So we didn't just do the design and call it done. We actually built the molds, molded the parts, assembled them, and then tested them. And we took 10 stamped steel parts that are welded down to 3 molded parts, bonded those together, sent those to Chattanooga. They put them on Atlas vehicles, sent them through the paint line, you know, where they saw temperatures of 400 degrees Fahrenheit, then put them out in the field, did durability testing, did all the other testing, and approved the material in the process. Since then, Volkswagen's implemented the technology on 4 vehicles, 4 platforms worldwide, including the ID Buzz, which is their new minivan that's coming to America soon. And it will also, we anticipate it will also wind up on the new Scout SUV and Scout pickup that'll be built in South Carolina and rolling off the line in 2026.
Great, thanks very much. And by the way, I saw one of those vehicles. They're pretty cool. Olivia Morales comes to us from CESMII. I love that acronym, by the way, CESMII. Olivia, tell us about what's the focus area for CESMII. What's your role in that organization? And then also, please give us an example where digital technology led to efficiencies in energy usage.
Sure, thank you. So CESMII stands for the Clean Energy Smart Manufacturing Innovation Institute. So you can understand why we shorthand it to CESMII. We focus on smart manufacturing, and I'm going to define smart manufacturing and talk a little bit about how we actually use smart manufacturing and apply it with our members. So smart manufacturing is effectively getting the right information to the right people to make decisions within manufacturing. With that comes education, training, technology, bringing together the right stakeholders with manufacturers and technology providers. We fund projects that actually build the technologies and apply them with those manufacturers. Clean energy is in the name, so each one of our projects has deliverables and objectives focused around energy reduction as the overall goal for the project. So it's not just developing cool technology, which we do, but it's also driving energy efficiency in the process and making sure that we're delivering technology advancements that are fulfilling that overall goal. One example of that is a team that used augmented reality in the manufacturing process for wind turbines. The training process was incredibly taxing and manual between short staff and not having access to the right information at the right time. The other problem with the wind turbine quality check was that they couldn't easily detect the defects in the material itself. But through the augmented reality, they were able to develop machine learning algorithms that actually applied computer vision and automatically detect the defects in the actual wind turbines. This was really impactful because they were able to cut the time in half to actually find those defects and cut the time in half for training. This also has a pretty big impact on the warranty claims, because they were able to trace back the quality through the augmented reality and they had actual results from those images. They saw a reduction in warranty claims, which saves them millions of dollars. So, in my role, I forgot to say my role, I'm a solutions architect at SESMI. So I'm the one that's bringing the people together to apply these technologies, develop good architectures that leverage information models, standards, making sure we're building future-proof architectures and technologies that are going to be able to work together, not just now, but in the future. As you know, with your smartphones, technology changes very rapidly, and we want to be able to apply the same sorts of concepts to manufacturing as well. The industry right now has a lot of small manufacturers, a lot of pen and paper in the industry. And that makes it a lot harder to get the right information to the right people. If you're depending on someone manually writing information, making sure that that manual information is correct, there's a lot of room for error. So we at CESMII are pushing for smart systems, smart architectures that are going to be future-proof, rooted in standards, and able to adapt to the dynamic landscape that we see within the technology.
Fantastic, thank you so much. And then Magdi Azer comes to us from an organization called REMADE. So again, if you could tell our audience what is the focus area of REMADE, what's your role in that effort, and then an example where digital technology was used to make an impact on the environment.
As Art said, my name is Magdi Azer. I'm the Chief Technology Officer at the REMADE Institute. REMADE Institute focuses on sustainable manufacturing of metals, polymers, fibers, and electronic scrap. And for each of those metals, those four materials, our goal is to create a circular economy. Now, you've probably, if you've been attending the energy track, heard that term a lot, but let me give you a little bit more of a formal definition. So in a circular economy, your goal is to create a closed-loop system where products or materials or resources you have can be reused or repaired or remanufactured or recycled in order to extend their lifetime and to reduce their environmental footprint. So each of us works for a DOE-funded institute, and for all of us, the goal is always around reducing energy and emissions, because manufacturing itself consumes 1/4 of all the energy that is consumed in the United States every year. So as far as an example, let me ask, is anybody in the audience today wearing either Adidas or Allbirds shoes? So we got a few folks. So we have a project that is running right now that involves Adidas and Allbirds. It involves a chemical company, Braskem, and it involves Massachusetts Institute of Technology. And it's focused on shoes. So when you wear shoes, the thing that makes them cushiony is a material called EVA rubber. Now, the problem with EVA rubber is once you've used it to make a shoe, it can't very well be recycled because of some of the properties of the material. In fact, the EPA estimates that around 15% is what the recycling rate is for that material. So these competitors got together and said, how can we find a way to recycle this material? And so working together, doing a lot of analysis, they found a way to change the chemical structure of that material so that they could recycle it. And so their short-term goal is to increase the recycling rate from around 15% to 30%, and long-term we're trying towards 70%. To give you a sense of why that matters, each year in the United States, we buy and use 2.4 billion pairs of shoes. So that's a lot of EVA rubber, and it's a big opportunity for us. Short-term, we'll save about 500,000 metric tons. Long-term, it'll be closer to 3.5 million metric tons.
I can't get that out of my head, this vision of billions of shoes. It really adds up to an awful lot of material. I want to just briefly touch on something that a couple of you said, bringing people together, competitors working together. This is the power of this kind of organization. This is a public-private partnership where, for the good of the overall industry and the nation, we get really strong competitors sitting side by side solving these very big problems for us. It's really very powerful. I'm going to go around. Oh, before I go on, I also want to tell you, please start thinking about your questions. We will make sure to have time for questions at the end, so think now. But I got some more. I'm going to go back to Dale. Dale, IACME really focuses in on advanced composite materials. So people may not be familiar with what that really means. So I want to ask you about what really is a composite material, what's it made of, and what has changed over the last several years to kind of change the capabilities to make it an advanced manufacturing process.
Sure, thanks, Art. So let's start out with, for people that don't understand what composites are, let's just say you have a set of fine china that's been in your family for a number of years, and you got to ship it across the country to your relatives. So you carefully package it up, and you put it in a box, and you look around, how am I going to seal this box? So you find a ball of twine, and you start wrapping that around it, and you tie it up as tight as you can, and you say, well, it's kind of loose, and it moves around. So the string isn't maybe going to get the job done. Because, do I really trust shipping this with the shipping companies, and it all staying together? Then you say, oh, I've got this clear packaging tape that I can use. So instead you say, well, I'm going to put that on there, the kind with, that shows up most people use, and you make sure you go down the middle and all the sides, and every single corner is all wrapped up, and by the time you package it up, you've used a whole roll of tape. But what if you had a solution, and all of a sudden you realize that there's this thing called strapping tape that has all kinds of reinforcement in the tape, and now you've got something that does the work that neither of the other two solutions could do by themselves. And so it's a very, very durable material. You can use that, and your package is going to arrive safely and not come split open anywhere, because that tape is really hard to get through without a pair of scissors. And that's what composite is. It's string and some sort of glue. So that's how we try to go simplify it as most. But the strings we work with are things like glass fiber, carbon fiber, Kevlar, some polymer fibers, and increasingly more natural fibers like jute, hemp, flax. And then the glue side, or the resins, epoxy, polyester, some thermoplastics like nylons and polypropylenes, and some more exotic temperature materials. And increasingly more, some of those are being made from bio-derived polymers. So, again, opportunities to lower that footprint. But we put those together, and that's how we get composites. The advanced composites tend to be the ones that are designed for the highest strength, the longest durability, and so forth. Composites are everywhere in your daily life. You may not even realize it. If you snow ski, you water ski, you ride a snowboard, you play golf, you ride a high-end bicycle, play tennis, racquetball, all of those are composite structures. The carbon fiber rackets, the fiberglass snow skis, and they last a very long time. They're very durable. They're in your daily lives. And then there's some when's the last time you saw a rotted or rusted boat at a marina? Composites. They're very corrosion resistant, durable. There are also places you can't see them. When you go to the gas station and pump gas, all of that gasoline is stored underground in a fiberglass tank that doesn't allow any of that fuel to ever find its way into the soil. Back in the days, steel tanks leaked and a lot of soil got polluted. And one place you certainly can't see, but is very important, is the whole backbone of the James Webb Telescope is made with high-performance carbon fiber composites. Could not exist, could not do its job without the use of composites, and what they do for dimensional stability for those mirrors and those cameras. Now, from a decarbonization standpoint, we at IACME work mainly on things like wind turbines, for example, which today, those ones, if you were or any of you were in the earlier session about offshore wind, are now growing up to about 107, 110 meters long. Put that in perspective. That's the tip of one end zone of a football stadium to the tip of the other end. That's how long those blades are now. All molded, assembled in one piece, and that's when they go offshore to be mounted, to be able to generate 12 megawatts of power. More and more automobiles are using composites, but airplanes. Composites have been on airplanes for a long time. In fact, the A350 and the 787 are both highly composite intensive, fuselages and wings of composite in those. Of course, we paint them and hide all that and make it look like aluminum, but they're 20% more efficient than their predecessors. We're making hydrogen tanks for storage of hydrogen to be used on heavy trucks and in airplanes and for transport. And then the last area I'll talk about is in infrastructure. A composite bridge, can last well over 100 years compared to your typical 30-year lifespan of a steel reinforced concrete bridge. So you think about the less times you have to use that concrete, which produces a lot of CO2 in its formation, but to save a lot of energy there. So it's just come as examples of where we are. But the big thing that we're doing is that transferencing is adding a lot more science to it. Right? You know, and so these materials have been around for, in some form or another, for 60 years. But it's in the last 20 years that we've been able to really make them advanced in the sense, not in terms of just performance, but in terms of how we analyze and design for them.
Yeah, thanks. I think that's a good point, and something I wanted to mention earlier. You were talking about digital technologies, and frankly, any modern manufacturing is all surrounded by digital technology. It just has to be that way if you're going to be competitive at all. Olivia, I want to ask a different kind of question, and it's something that's being talked about a lot here at South by, which is artificial intelligence. Now, there's artificial intelligence, and sometimes some of us will also lump that in with machine learning. But maybe you could talk about how those differ, and also how those things can be applied to modern manufacturing and impact not only energy usage, but other ways to make manufacturing more efficient.
Yeah, thank you. So artificial intelligence is a broad topic. Fundamentally, it is some sort of system or software that's mimicking something that a human would otherwise do, often more efficiently or more automatically, but that's sort of the overall goal. Then machine learning is a subset of that, or an application of AI. It uses training data and algorithms to produce results and come to some sort of conclusion that, again, can be producing some sort of word output, imagery. It can be statistical analysis, but it takes the training data and it gets smarter over time. Thus, the machine learns. In manufacturing, there's all sorts of applications for this. One was the wind turbine example that I explained earlier. That one leverages a digital twin, which is a virtual representation of some sort of asset or process, and uses the data that comes in from the imagery, trains it through a machine learning algorithm that it's trained on the actual video and photographs of the defects, and then produces a result. It produces a visual indicator of where the defect actually is and how large it is, quantifies it, anticipates the impact that it's going to have on the overall wind turbine. There's other areas where you can apply machine learning and AI, for example, soft sensing, which is being able to use sensor training data and anticipate that sensor's value in the future. A lot of manufacturing processes depend on destructive or expensive measurements to be taken to prove out the quality of the actual product that's being produced. But wherever you can reduce the need to actually take that physical measurement or expensive measurement, the better. You want to be able to anticipate the quality and perhaps even make adjustments to the process before actually impacting the outcome. In that way, AI and ML can affect control. You can feed you can create a closed loop system where the current sensors and the current quality measurements can then feed back into the control loop and affect the process and the outcome without you needing to actually physically tell the system to do it. You can depend on the algorithm to do it for you. Those are just two examples, but there's a lot of exciting work that our teams are doing to do research on where we can apply the different areas of machine learning and AI. Training is another great example. We have a team that has developed training modules that leverage AI to work with new employees who are new to manufacturing, who are new to a particular process. Ask questions to a bot similar to your Google Assistant or Siri, get results from that, that's AI. And that speeds up our ability to train new users and educate them and then inform the machine learning and the AI algorithms and make them better. So maybe one day they can solve some of the higher level problems that we're looking at.
We've got a question coming in from the audience. I'm really excited, so please go ahead.
Yeah, I want to break it up. Thanks for letting me jump in here
Yeah.
real quickly. It's been a few years since I've looked at models for like life cycle analysis or assessment. I usually go to like Argonne National Lab and things like that. Back then it was very traditional methods on how they would, and there was arguments, of course, on which one. So I was wondering, this is great that we have new ways to actually see how we can make things more efficient. I was wondering, are you guys using proprietary type estimates in-house, or are you feeding this in with the national lab and they're incorporating this so we have almost like, I don't know, a centralized assumption base on where we can actually compare these types of efficiencies?
Do you take that one?
You start.
So I'll tell you what the REMADE Institute did. So we've had projects where they did the formal life cycle analysis. You know, they established the boundaries for the process and what are the inputs and the outputs. What we realized when we started up REMADE is very few people have background in life cycle analysis. So we built a simple Excel tool that essentially looks at the difference between the energy it takes to make a new aluminum, let's say, and recycle aluminum, and then based on the change in energy and maybe changes in mass between the before process and after process, it gives you kind of a first order estimate. So it's not rigorous, but we wanted to at least give our teams the ability to directionally say, this is more energy efficient, or you save more energy with this process than another process.
Yeah, I want to address another question that you had about that, was about how much of this stuff that we work on becomes proprietary. In all of these things, IP policy is incredibly important. And when you're bringing competitors together, it gets even more sticky. But if you have the right policies and you have enough of these understandings up front, you can get people to the table and they'll work together for the betterment of the whole industry. So it was a great question, and I wanted to address the IP part of that.
Yeah, I just want to add one thing is, you know, we're working on life cycle analysis for lots of things, you know, and with composites, sometimes the embodied energy that's involved in it might be a little higher in the out the door, but over its lifetime, it uses a lot less energy. And so it's very important to understand if you've got something that, you know, an airplane that's going to last 40 years, you know, how much less fuel burn is it going to have because it's lighter? And then, you know, and then obviously the other thing about that is that information needs to be public, you know, and it needs to be audited, and it needs to be believable, because, you know, it's very easy for anybody just to pull a number out of thin air. So there are evolving databases that are public, and our intention is to continue to make that data public and show the supporting calculations and analyses behind them.
Yeah, I appreciate that. Just to come back, I was from the automotive industry. So before we were doing it, just like natural gas versus diesel versus petroleum hybrid.
Yes.
So we'd compare larger macro chunks like that. But now that we have new materials and lightweight and things. So that was my background coming into that. But thank you for addressing that.
Thank you. And by the way, anybody, take the mic if you have other questions. We'll continue on, but if you're got some burning question, we want to answer them. So take the mic whenever you want. I'm going to jump back to you because I just want to. There was a term you used, and I want to go back to it to make sure people understand it. And then there's a little bit of a tidbit I think you shared with me a while ago. And the term is remanufacturing. I don't hear the word remanufacturing very often. And what you told me in one of our earlier conversations was how important it is to think about those sorts of things at the very earliest stages of design. So maybe you could talk about remanufacturing and the importance of design.
Sure. Well, let me say, let's compare things a little bit. So if you repair something, let's say you've got a leak in your toilet, right? You maybe put in a new gasket or something so it stops leaking. That's a repair. When you remanufacture it, a product, you're actually returning it to the same capability and functionality that it had when it first came out the door. So you're essentially extending its life to go another life at least, and oftentimes 2 and 3 lives past that. So that's the value of remanufacturing. And the reason it matters is because if you compare remanufacturing to making a new tractor or some other kind of component, you're saving somewhere between 80 to 95% of the material that you would have to expend if you were making a brand new part, and around 80 to 96% of the energy. So there's a big benefit there by remanufacturing.
Great, thank you very much. I'm going to continue going around the panel here. From some of the attributes of advanced composites that you talked about, you know, we're making things lighter, so we're making it easier for whether it's an automobile or an airplane or whatever it might be, and it's lighter and it's stronger, so the sort of ratio of strength to weight is really a big factor here. Sounds great. So what, if anything, are the barriers to enhancing and using more composite materials? And then sort of the flip side of that that's related, if all of a sudden now composite materials take off and now everything is composite, what do we need to do to prevent that from becoming now filling all of our landfills eventually?
Yeah, I'll start with the first barrier, and there's three barriers that I see in terms of getting composites in the marketplace. One, a fellow at BMW who was the father of all the carbon that was used on the i3 and the i8, and then later on the 7 Series, you know, and he says at the end of the day, the only technical parameter that matters is cost. You know, and that's true. These materials have to earn their way onto the platforms in which we use them. On a wind turbine, it's very easy because composite materials are the only thing that can produce something that can last 200 million cycles in the field, you know, of fatigue cycles, and at that kind of mass and weight and deliver that kind of energy. But if you look at an automobile or an airplane, you know, you have opportunity, you have aluminum, you have steel, you have things that are inherently less expensive to start with. So we have to continue to drive down the cost. First thing we do is better design to remove the amount of excess material that we put into it, you know, because we lack confidence fully in it. Second thing is reducing the manufacturing cycle time, and the third thing is reducing the scrap. Okay. You know, another barrier that I see a lot is access to capital to get out of. You know, when we talk about the valley of death, there is the technological valley of death. There's a financial valley of death for a lot of entrepreneurs to get to the scale-up stage and so forth. So we have to find ways to get more hard tech investors into the marketplace. And then the third one is the talent pipeline. Okay, those are the three barriers there. Now, you know, some of you may have seen, you know, a couple of years ago, you know, pictures in Bloomberg of wind turbine blades being buried in a field, you know, in the plains of Wyoming. And people say, ooh, you know, these things are great at delivering clean energy, but they become waste at the end of their 20-year life. And so we've spent a lot of time, you know, since 2015, when we were founded, in learning how to better recycle composites, whether that's to repurpose the materials, you know, I mean, grind them up and then, for example, mold them into shipping container floors, which today use exotic tropical hardwoods. You know, so we can replace old rainforests with these materials and make them infinitely recyclable as well to keep them out of landfills. But the landfill, you know, problem is not as great as one might think, but it's still important for us as an industry to continue to find ways to fight that. I mean, relative to, say, coal burning plants and coal ash, we make, you know, the total amount of composite scrap and waste in the world, you know, whether it's end of life or process related, is 1/1000th of that, of the tonnage of coal ash produced every year.
Yeah, it's great. And you also brought up something I want to share with the audience too. You talked about the Valley of Death. I mean, that's where we live. That's another real purpose of these institutes. We're trying to get these capabilities and these manufacturing technologies through that Valley of Death. And you know, if you're into all the technology stuff, you know, we're talking about things that are like a manufacturing readiness level of like 4 up to 7. You're taking things that are kind of just coming out of the lab but not really ready, up to where they're actually ready to go into at least pre-production manufacturing. So a good point on that. Now, you talked about barriers of entry. I want to now flip the question to Olivia. One of the phrases that we were chatting about was, you know, if you're not doing smart manufacturing, you're not doing it right. But there are barriers to doing it. And maybe you can share that, because it seems like, well, why wouldn't you do it smart? What are the things that prevent us from making all of our manufacturing more smart?
one thing that I find time and time again with our members and our projects, people are excited about smart manufacturing. They want to implement smart sensors or information models. They want to use cool algorithms or have apps that are going to deliver them value, but they don't know where to get started. And they kind of feel like they have to get started with everything all at once. And then that becomes expensive, and how do you know if you implement it and you spend all of that time and all of that money implementing it, if you're actually going to get value? And so one of the things that we've been focusing on in the Institute is pushing for more incremental changes, adopting, maybe start with whatever feels most feasible or a use case that feels really tangible and you have the expertise within your team to start applying it. That could just be adding a sensor to a machine and starting to get that data into digital format instead of having someone go and look at the temperature reading and write it down and write down the time of day. Have that data starting to stream in. Stop there, just be able to visualize that data. It's a great place to start. We want to help our manufacturers avoid getting into pilot purgatory, into that state where they've tried out a few different types of technologies, but it's not ready for production. It's been expensive to implement it as a pilot, and it's hard to get business buy-in to deploy it to more plants. I had one manufacturer come to me. They were part of a research and development group, and they'd been trying out really cool concepts, applying standards, and they came to me saying, hey, how do we convince our bosses to start deploying this across the entire enterprise? It was a large organization, and they had many plants all over the United States. I told them, don't. Maybe start with one plant. Get the leadership buy-in, start implementing some of the concepts that you've been developing in a lab. There's no reason to do everything all at once. It's expensive, and by the time you plan it out and start implementing it, the technology might have changed. You need to be agile in your implementation of the different technologies, or else you're going to get stuck in the same situation that manufacturers are in today, which is they're stuck with architectures that are not flexible, and they have vendor lock-in with a particular technology provider. It makes it really expensive to move forward. For our small and medium manufacturers, which makes up 74% of all manufacturers in the United States. So 74% of manufacturers have 20 people or less. And so then cost also becomes really a significant factor. CESMII's role in that is to de-risk the implementation of some of these technologies. So we provide some funding for projects, connect them with a technology provider who has some expertise in smart manufacturing, and start driving some innovation and start gaining some confidence with the concepts before they have to put forth too much of their own capital and time. Along with that goes training. One of the main barriers to even thinking about applying these technologies is not having the right training or expertise on those teams. If you only have 20 people that make up your manufacturing organization, how do you know that any one of those individuals is going to have the right training to apply these new concepts? So we focus heavily on education from high school and middle school all the way to current workforce development to make sure that we are upskilling and bringing in the next generation of manufacturers with the right skills to apply these concepts.
Great. And you guys keep bringing up terms that spark things in my mind that I want to share with the audience. You use the word de-risk. And I think that's another really important part of what we do. You know, in my world, there's a lot of people interested in what we do, but they're kind of hesitant because of the capital requirements, right? Like, I don't know, I'm just not ready to invest yet. But they can come to us and say, oh, now I get it, why this piece of equipment might be good for this, but maybe you'd rather have this one. And we share that openly with our members. And so it de-risks a lot of their investment. The other thing that you were talking about was the architecture of some of these tools and the manufacturing line. If you think about a classic manufacturing line, you've got machines feeding machines, feeding machines in terms of parts. But then think about if they're feeding not only the parts, but they're feeding information. Saying, this is what I saw, now I'm handing it to you, now you can do something about it. But this is really great. I see we have another brave soul who wants to ask a question, so please go ahead.
Good afternoon, I'm Adam from Autodesk. Your smart factory really is something we're aligned with, speaks a lot to the stuff that we do in our software. I manage 3 workshops for Autodesk in North America. So we have workshops that actually have machines in them. We're using our digital tools to drive the machines. And during COVID, our shops were pretty much shut down. So I had a team of 24 very skilled technicians in multiple areas of fabrication and machining and manufacturing. And we needed something to do because we didn't have any parts to make or research to do. So we started putting sensors in our workshops, starting understanding, how can we digitize some of the manual processes in our shops easily. And the focus is really to democratize it for our users and to understand some customer empathy. So we started with simple things like just putting a sensor on an air compressor to understand what the compressed air system was doing. And then it can go out and build out from there and talking about machines. So I think you talked about 74% of the manufacturers in the States are small and medium. So I think it's really important for those organizations to understand how easy it is to start digitizing and taking small steps. Another thing that we found out by doing this exercise is we work closely with manufacturers of machine tools like the Mazaks and the Haas's and the Renishaws of the world. Some of the challenges that they face is that they have their machines already stacked with sensors, data output capabilities. We have one Renishaw machine in our Boston facility that can put out 1 terabyte an hour of data. But the challenge that they're finding is that they don't know what to do with the data. So if CESMII can help define that with the manufacturing base and with the manufacturers, I think that would really take a lot of steps in moving these technologies forward.
Yeah, you make a lot of good points. And the CNC example is a great one. We have a bunch of members who are using and building things with CNCs. And one of the challenges to actually being able to use the data that's coming off of these machines is there's no standards around what the data actually needs to look like, right? It's stacked with sensors, there's a lot of data coming off of it, but you might have 2 CNCs made by the same OEM, and the data coming off those machines looks different. So one of the things that CESMII is trying to do is bring together competitors, application developers, technology providers, manufacturers, to help standardize what the information even looks like so that an application developer, whether that's a visualization application or an ML algorithm, can actually be built against an information model that's been standardized, and then the manufacturer doesn't have to worry about the actual transport of the data or what the data is called or what the naming convention is that maybe the OEM came up with or the systems integrator came up with, trying to extrapolate the actual meaning of each data point and have applications built against that.
I think if we're going to really close the loop, which is the holy grail, right, we're going to need to be able to standardize a lot of these things. So thank you so much. Appreciate it.
Yeah, I appreciate your comments too, because I remember years ago thinking to myself, there's sort of like these 2 classes of engineers, the ones that collect mountains and mountains of data and never do anything with it, and the other ones that collect like 1 or 2 pieces of data and extrapolate to the end of the universe. It's just not right. Both Dale and Olivia talked a little bit about barriers, but I want to ask Magdi about, in terms of circular economy, are there models or are there people or countries or geographic locations that are leading the way that we ought to be considering learning from?
Great question. I would say there's a lot more emphasis on circular economy and thinking about circular economies in the EU. They seem to be more proactive. And they're not just looking at manufacturing, they're looking at how do we, Rotterdam is trying to look at how do we make a circular city where everything becomes a nutrient for the next cycle. And so I would say the Europeans are a little bit ahead. But everybody's interested in that concept.
Fantastic. Any other questions from the audience? I can go all day. It doesn't.
I want to piggyback off the EU point, though. So CESMII also works with, we're US-based, we're funded by the Department of Energy, but we recognize that our manufacturers and technology providers are going to be international. And so we work pretty closely with some of the standards organizations out of Europe, and especially Germany, because they have pushed forth many standards that actually drive the level of data contextualization that we are looking for. So we work closely with them and try to apply some of those concepts within our own institute. Institute. They've also launched a new initiative recently for the exchange of data across the manufacturing supply chain, which is another really important application of these digital technologies and information models and data contextualization. We need to be able to share data across the supply chain to be able to come up with the same algorithm development, same flow of information to the right people. Something that happens early in the supply chain, like material quality, is going to have a big impact down the line. And if you can find that out as a manufacturer earlier in the process, the more able you're going to be to modify your process accordingly.
Very good. Got a question?
Thank you guys for speaking on this. Part of why I was here was to hopefully hear a bit about digital sustainability. I think I heard some components in there. How do we take digital and sort of improve our sustainability efforts? For example, using like sensors, we kind of touch on those things. What are we currently doing with power and energy? And then how do we know to change what we need versus what we're currently doing? If anyone can kind of speak more on that, how do we use technologies to actually improve our sustainability efforts? Thank you.
I can start. So I think the first step is being able to have access to that data. So having insights into what part of the process is having the highest impact on your overall energy consumption, for example. And then having that inform the rest of your process. And even as a consumer, maybe having access to that level of information so that you as a consumer know the impact of your decisions on the rest of the energy consumption. So being able to capture that information, have it easily accessible for the decision makers at all levels of a manufacturing operation, and then to the consumer to make their own informed decisions as well.
Yeah, I'll comment as well. When I was young in my career and there was no gray hair, I had a senior manager that said, "What gets measured improves," and I think we have to remember that. As long, and that's true. It's true whether you're applying it to personnel and KPIs and so forth, but it's also, to your processes and to your products. And if you're measuring how you're making your products, in our case, we've got increasingly more and more sensors that measure things like temperature, pressure, degree of cure, and so forth, because every mold is in essence a chemical reactor. A lot of people don't realize that, is every one of those molds has got a reaction going on inside of it. And by measuring those things, we can improve the carbon footprint of that by using less energy to make it. But then also more and more of our products have the opportunity to be embedded with sensors that tell us how they're doing during their life, when they need to be replaced, whether that's a wind blade that tells us that, hey, I'm not quite as rigid as I should be here, so whether it's from a bird strike or big hailstorm or some other damage, or rain erosion, or compressed gas tank, that's hauling hydrogen through all of these cycles, is saying I'm stretching a little further than I used to, which might indicate that there's some strain going on or some disbonding going on. And basically be self-reporting and letting people know that maybe time to inspect me or replace me.
No, it's a good one. And for us, we refer to that as structural health monitoring. It's incredibly powerful. It's coming. And if you think about it, combine, this is one of the cool things too. You start to combine these ideas where you say, hey, maybe I could print that and I could embed that into a wind turbine blade, and I could use digital technology to pull all that data out and feed it back without having to have wires all over the place. So there's a lot of crosstalk that's generated amongst the institutes. Not enough. We need to do more of that. But I think it's really it's very beneficial to everybody. And the nature of the public-private partnership just strengthens it by so much.
Can I follow up on?
Yeah, please.
So mentioning structural health monitoring or whatnot, we've got a tire manufacturer who's doing the same thing because they're trying to find ways to recycle tires. And one way other than recycling tires, you can remanufacture them, retread them, and do things like that. And they don't always know perfectly when to do that. So they're doing telematics within the tires to embed the sensors to tell them, do I do something, or can I let them go? And they're testing them out on commercial, like semis. because they do a lot of miles.
Yeah, and I think you told me too that that's a really tough problem because there's so many different types of rubber in a modern tire. Is that right?
Yeah, before I had learned it, I thought, okay, rubber is rubber. But in a tire, there's like 42 different formulations in a tire, whether you're talking about the sidewall or you're talking about the tread or other parts of the tire.
I mean, so many of these things that we take for granted, and there's a lot of complexity in something as simple as a tire. And shoes, I find out too. We have a question. Yes, please.
Good afternoon, guys. I'm currently working for OCI Global. I don't know if you guys heard about them. We're currently building OCI, a clean ammonia plant in Texas, which is going to be the largest clean ammonia in Texas. I wanted to ask you a quick question, being in HR. How do you fight, or how do you tackle the talent war out there, especially in manufacturing? Because that's something that in my department we've been facing and trying to tackle pretty heavily, but it's still difficult.
Thank you for the question. I was really excited about that. It is no simple silver bullet, but I will tell you this. Our approach, one of our principal approaches, is feeding the funnel. We don't reach people at a young enough age to make them understand that this is a super cool opportunity. And it's fun because when you get young kids involved in it early enough and they see the capability and they start to ask questions like, this is so cool, how do I get a job here? That's when you've sparked that imagination. But you have to attract, you have to train, and you have to retain, right? So even going back and re-educating the existing workforce on what is the possible. And so we're developing programs. We've got an incredibly successful program in K-12. We're building out programs for returning military and for retraining people who need to have that extra spark to become and to continue to be productive as our manufacturing capabilities evolve. I'm going to check and see if we have 5 minutes? Okay, cool. Yes, please, question.
Hello, I'm Robbie. I lead Teralytic. We are the co-pilot for industrial supply chain decarbonization. So not necessarily working inside at a manufacturing facility, but helping figure out how you can go beyond an LCA to actually implement change and finance that with your suppliers. I would like to think that we're one of the innovative digital solutions out there, but I actually would just love to hear from each of you about what's just one interesting digital problem that you saw being addressed outside of your four walls, whether it's a startup or something else.
I want to make sure I understand what your question really is.
I would love to hear about, just interesting solutions, startups, et cetera, that you all have seen that just creatively take advantage of digital in other manufacturing facilities.
Yeah, I got. Okay, go ahead. Sorry.
So the way that we process municipal solid waste in this country is oftentimes it gets picked up curbside at your home, gets thrown into a truck where it gets mixed with everybody else's trash, and so you create contamination. And in fact, about 25% of the trash we collect is automatically thrown out because it's contaminated. And so a couple of the projects we have are with small companies who are trying to turn that model upside down and make, if you will, smart trash cans, so that if you're at a stadium and you're walking out, you can put your trash in that, and it will automatically sort the trash, avoiding that contamination. So you're not putting a dirty pizza box with paper or something like that. And so they're trying to go to these models of resource recovery that are at a smaller scale. And so they're having conversations with different football facilities, baseball facilities, about putting these in place. And of course, the other benefit, other than the technology, is the price point is so much lower, because to start up a new material recovery facility, you're talking about $50 million in capital investment.
I'm gonna jump in. I know we've been getting waves from the back of the room, and I'm just gonna encourage you all to. We're happy, at least I know I am. We're happy to stick around if people want to ask us some more questions. But I want to not forget to share with you this. You can take out your phone, take a snapshot. Please do. There's some great information on not just us, but the overall Manufacturing USA network. And reach out to any one of us. Our contact information is readily available, and we love to tell the story of Manufacturing USA. I'm going to let now our panelists just briefly, very briefly, give any last thoughts that you might want to go through, and let's start with Dale.
Sure. Thanks. I want to say thanks to all of you for being here and being patient. Again, I'll be here after, and more than happy to sit and chat with you about the beauty of composites and how much fun they are to be in, as well as any other topic you'd like to discuss. But I just, as everybody here knows, I landed last night coming back from a week in Paris, where we have the annual world's largest composites trade fair with over 40,000 folks there and 1,500 exhibitors. And the takeaway is you come away from something like that and you look at what's going on in the rest of the world. Other people are working on the same kind of problems, and solutions, whether it's in wind turbines or lighter weight vehicles or hydrogen storage and transport. Saw lots of cool innovations in infrastructure applications using composites, lots in novel materials based upon natural fibers and natural resins. But it also gives us a chance to talk to the folks in other countries that serve much of the same purpose we do, the other institutes. So we sit down at these annual events and talk to our friends in Germany, in the UK, and in Korea, and understand what their funding models are, what they're working on, and so forth, and what the issues they see are. And of course, one of the big ones everywhere is workforce, continues to be. The other one is how do we make sure we have the right image out there, because composites, while they may be technically single use, if you think of single use in the terms of 30 to 50 to 100 years, they're not the same thing as a styrofoam container or a plastic bag. And so there's a real difference there, and people need to appreciate that. And then it also makes me feel like we really need to make sure that our countries continue to invest in advanced manufacturing so we can remain competitive on the world stage with all the countries that are there. And believe me, there's a lot of money flowing into these technologies elsewhere, and we need to stay competitive.
Olivia?
Well, hopefully throughout this session you've gained some insight into what is happening within manufacturing and how the U.S. is funding innovations within manufacturing. But we're just 4 people from 4 different institutes. It just represents a sliver of the innovation that exists and can exist within manufacturing. There was a question about attracting talent, and I know that I was one of the folks that early on in my career wasn't that attracted to manufacturing, and the more I learned about it, the more I worked with it, the more I saw of it, the more interesting it became. The constraints make innovation that much more exciting, I think. And hopefully you guys have learned a little bit of where those innovations are currently and where we want to take it in the future.
Thanks. And Magdi?
Just as an anecdote, I'm a little bit like Olivia. The 2 classes I hate, I'm a mechanical engineer by training, the 2 classes I hated the most in undergraduate were manufacturing and material science. And so I think God has a sense of humor that I've spent my entire career in manufacturing and material science. It also speaks to the power of a good teachers. I think that what I would say is, or my tagline would be, you can't get there from here. And what I mean is, we often hear about the road to net zero emissions, and there's this impression out there that it's all about going to clean energy technologies, solar and wind and all of these things, and those alone will get us to net zero emissions. And there was a study done by the Ellen MacArthur Foundation, and they found out that you can only get 55% of the way to net zero emissions only by clean energy technologies. That you really have to focus, the other 45% of the way you're going to get there is through materials and manufacturing. So if you look at 5 materials, polymers, steel, aluminum, cement, food systems, and plastics, that is almost half of that 45% I talked about. So how we consume materials, how we do it efficiently, is the only way we will ultimately get to net zero emissions in concert with the others.
All right, I want to thank our speakers. Maybe we can give them a round of applause. And thank you so much. Come and find out more about Manufacturing USA.